Hello, welcome back to Rotary Rockets. Today we have part 5 in our series of making our biggest rocket motor ever. Now this is using the same casing we used in video number 4, so I'm not going to cover the details of the construction of this. If you want to take a look at that, you can go back to video number 4 in the series and take a look at that. While you're at it, take a look at the other videos too. 1, 2, and 3 are also really neat and show some interesting designs that didn't work out so well, including this one here. So we did manage to get from this to this. And it is a nice casing. We had a nice ground test. We did get some heat discoloration up at the top, and that's what we're going to try and solve today. So we're hoping that really didn't do any damage to the steel and it still holds up well, but we don't want that to continue happening and overheating the casing. So as we showed in the last video, we're using a PVC liner. This is 1.5 inch PVC, 18 inches long, that slips into the motor casing. Now, in order to stop heat from going up there, we purchased some 1/4 inch thick PVC flat piece and used our CNC machine to mill out these little caps. And those fit beautifully onto the top of our liner. So that will slide up, and that will be the protection for the top of the rocket motor casing. We're going to glue that on with PVC cement after we fill this with the rocket fuel, so that should hold on nicely and be a good protector up there. So one of the major differences we're going to try today, if you take a look at video number 4, if you've already seen that, the thrust was a little weird on that particular motor test. Now that used 5 individual fuel cells inside the liner. And what we got was a very high amount of thrust and then a very small amount of thrust, and then it was done, which is a very weird thrust curve for this type of motor, and it's certainly not the most efficient thrust curve, and it's not what we were going for. So one thing we're going to change today in our first test is, instead of using 5 fuel cells, we're going to load this up with 1 solid fuel cell. And that's our Flexi Fuel mixture, which is potassium nitrate, powdered sugar, and corn syrup, also known as Flexi Fuel. So as I said, this is 1.5 inch diameter PVC, 18 inches long. It's going to have a 1/2 inch core hole cored through the center of it. So we'll go ahead and get that loaded up, and we'll be able to do a ground test with the single fuel cell. Now, depending on how that works, we may be moving on to another test where we're going to change the mixture of the fuel to try and adjust the burn time. So this is the first test with the single fuel cell, and depending on how that goes, we may move forward. We'll take a look. We've got the fuel poured in there, and we use PVC cement to glue on the end cap. Now I just wanted to touch on two reasons as to why we're doing the solid fuel cell instead of the individual fuel cells, because anybody that's watching this would normally know that this is typically a Bates core motor, which would use individual smaller fuel cells or fuel cores. So the 2 reasons is we want to see what kind of burn rate and therefore thrust curve we get out of the 1 fuel cell as opposed to the 5 fuel cells. And the main reason is simplicity. It's just a pain in the neck to pour 5 individual fuel cells. We have to have 5 jigs, we have to mix the fuel up, set them all into the jigs, and then install them into the casing. It's just a pain in the neck. So what we're hoping is, if this becomes one of our standard motors, we'll be able to cast this just in 1 or 2 pours just to get the thing done faster and have it ready to go. So it's really a simplicity issue. So all that's left to do now is to install that into the motor casing. We'll get that set in there, and then we'll get some pipe thread on the threads and thread on our nozzle. Alright, so that went really well. The casing held up just fine. there's no more discoloration on the bottom here any more than there was already, so we didn't get any heat issues there, and no heat issues up at the other end either. So that casing held up fine for the second test. Now we took the liner out. Now this is the bottom end where the nozzle was, and we do have some blackening here, so we did get some blow-by that came around the PVC and tried to go back up the casing. And that was kind of expected because that nozzle was actually designed for an older design of the casing, so it doesn't seal tight up against the PVC. It's kind of a little bit bigger, so it allows for some gases to go around there. If we make this one of our permanent motor designs, I'll redo a new nozzle that'll be pushing directly up against the PVC, so that won't happen. But it didn't cause any problems on the casing because in that area it's just a large mass of steel, so it can really handle a lot of heat, and that blow-by down in that area really didn't have any effect on that at all. So that's good. So the big question was up at the top for our little cap piece that used to look like that. It does have a little bit of a hole in it, and it's melted. Now, it's a little difficult to tell whether that was actually an issue that occurred during the burn or after the burn. I tend to think that it held up just fine during the burn and that this was after the fact. And you have to bear in mind, when we were testing it, the motor is upside down with the nozzle facing up. So any residual products that are in here, little bits of fuel, whatever, that just don't get ejected right at the last millisecond of the burn are just simply going to fall down to the bottom and just sit down on that plastic piece. And that is what I think actually burnt through. We had to bang a little bit on the crust there, but we did get through on the bottom. So I don't think that's actually going to be an issue, especially when the motor is in its proper position. So I really feel good about those caps. It held on perfectly fine. The glue is still completely intact, and it didn't try to blow through between it. So what did we get for thrust out of this? With that single fuel cell, you see the thrust was very consistent. We had a really good burn rate for the entire time. We reached 254 pounds of force at 0.86 seconds. And up until that point, it was there was a little bit of a bump in the thrust curve, but it was pretty consistent. And then we reached back down to zero thrust at 1.7 seconds. So that's a really long burn rate for this, and it was a pretty good burn rate. It was really what we were after compared to the previous one where we had the multiple cells and we just didn't get a really good consistent burn. So the ease of making the single fuel cell and the results that we got really show us that this is what we're going to be doing as far as this motor, is just the one fuel cell. So for our next test, what we want to do is try to slow down the fuel. Now, if you slow down the fuel, you're going to reduce the amount of thrust, but we don't need 250 pounds of thrust to launch the rocket. So slowing down the fuel will give us a longer burn time with less thrust. So we're hoping that maybe equates to higher altitude as well for rocket launch. And when we actually get into the real world of launching with this, we'll test that out with the normal fuel as well as the slowed down fuel if this test works good. So how are we going to slow down the fuel? Flexi fuel tends to burn extremely fast, and that's some of the problem of what we've had in the past with exploding casings, because it does burn so fast. So now that we're past the exploding casing part, we need to put an additive in the fuel to slow it down. So what are we going to put in the fuel? We're going to put in baking soda, which is sodium bicarbonate. Now, why are we putting in baking soda? To be honest, I have no idea. I read this online, that it was an option to add in to slow down the burn rate. A lot of times you'll read about people increasing the burn rate, adding things to the fuel, whether it be iron oxide or several other additives that they add in to increase the burn rate. We have no need to increase our burn rate, so we're going to try and slow it down. So this is one thing that we read about that is a possibility. we're going to try, just as a guess, adding 20% or substituting 20% of the fuel for this. So that does mean that we're going to have 20% less fuel in the motor to begin with. So in theory, we should end up with 20% total less thrust. And then we'll also be having less thrust simply because it'll be a slower burn. But that's okay. We're going to go ahead and cast another fuel cell for this. It's going to be a single fuel cell, exactly the same as what we just did. 20% sodium bicarbonate. And we'll do the same thing, a ground test, and we'll take a look at the results and compare that to what we just got. Is it recording? Mm-hmm. Okay, so got the baking soda in there, and it's definitely acting really funny. It got really dark right away. We're still about 20 degrees below where we want to be. It's only about 210 degrees. It's super foamy, super airy. So, yeah, we're still not up where we want to be on the temperature. This is really some weird stuff. So, not sure where this is going to go, but we'll keep going and see what happens. This continues to grow even as we've taken it off the heat. So this is not pourable. So we have an interesting experiment here. We're going to let this cool off a little bit, and we'll just do a burn test on the ground just to see what this does. But clearly baking soda was maybe not the right product to add. We'll show you a burn test on this after it cools down in a little bit. Well, it's not getting any smaller, so we're going to make some piles here. Let them cool off. Hey, that looks like something a dog would put out. So, yeah. Oh my gosh. I don't know. That was crazy. Oh boy. Alright, so it's had some time to harden up here. We rolled a couple of them into some interesting shapes. That wasn't really done for the joke of what you see. That was done because normally when we do a fuel test, we like to have a little stick of it so we can light it from one end and watch it burn to the other end. Let's go ahead and just see how this burns. So there's still a lot of air stuck in that even though I tried to compress it. But clearly it's burning ridiculously slow compared to normal flexi fuel. So just judging from that observation, I would say that's too slow for the rocket fuel. We're probably not going to get off the launch pad with that small amount of thrust. So whatever we do, we're probably going to go less than the 20% substitute for the fuel. So we'll go back to the drawing board and think about some other additive that we can try, and maybe do a smaller batch instead of this large batch and waste a lot of product. But we'll go ahead and burn the rest of this just to get rid of it. Okay, that was bad. It was funny, but it was bad. I don't know where I read online about adding baking soda to the fuel mixture. It was a long time ago, but clearly that was some bad advice. I think essentially we were making cake batter there for a while. So, lesson learned. That's what we're here for. How about we try cornstarch? I think it'll be a much more neutral additive. It shouldn't add any leavening or air like the baking soda did. And it really shouldn't add anything to the combustion, so that's exactly what we're trying to do, is just reduce the combustion rate. Which, interestingly enough, the baking soda did drastically reduce the combustion rate, but clearly wasn't usable. Let's give that a try, and we'll take a look at that fuel. So we kept out a little piece of leftover fuel from that last batch with the cornstarch. We're just going to take a look at how that burns. Okay, so right off, I would have to say that's a bit of a problem. That's 20% substitution for the cornstarch, and that is a really, really slow burn. Alright, that's that amount of time. That's not even half gone, so we'll just stop there with the video. Alright, so we really liked the results of that. The fuel mixture was very similar to what it normally would be as far as consistency. It cooked up nice, it poured nice, but that burn test that we did with the little piece, that was super, super slow. Way more than what we wanted. Now that was a 20% substitution of the dry ingredients for the cornstarch. We're going to reduce that down to a 5% substitution of the dry ingredients for cornstarch. We'll try it again and see how that works. Okay, so that fuel cell is all done and sealed up on the top. Now originally we were going to do a 5% substitution with the cornstarch. We talked it over and we really felt that we needed to go a little bit more so that we could definitely see a difference in the performance. So we changed that up and we went with 10% substitution of the dry ingredients for cornstarch. So hopefully that's going to show us some type of a significant change in the burn rate and the thrust curve. So we're ready to load this up and then we'll head out and do a ground test. Alright, so that was a bit of a success and a bit of a failure. It did show definitely that we are able to slow down the burn rate of Flexi Fuel with the cornstarch additive. Just taking a look at the liner here, this end here down at the nozzle end did definitely get destroyed quite a bit, but that's really to be expected because of the amount of heat and force that's going on down at that area. And it's okay for that liner to be damaged in that area because it's in the thick section of the housing, so it really doesn't cause any issues to the exterior housing. The top area, where we have the cap glued on, the cap is still fully glued on, although very deformed, and you see that we have a large gaping opening here from the heat. There's a thick layer of residue in there. There's actually no opening or no breach there from the inside because this residue just formed a hard skin there. And again, that may have happened after the burn was done, just from the residue falling down because we're doing the test upside down. So not really too worried about that, especially if it's happening afterwards. We don't see any additional heat damage to the steel up here, so I don't really think that's becoming an issue. So I still like the idea of the end cap being glued on. So comparing the two burns of the original single 18-inch long Flexi fuel cell to the one that we just did, which was identical in size but had 10% cornstarch added. Now on the original one, our burn time was 1.65 seconds, and we reached a total thrust on the scale of 254 pounds, which is pretty impressive. With the additive of 10% cornstarch, we went to 4.65 seconds. So that's a difference going from 1.65 to 4.65. Unfortunately, we suffered a lot in the thrust. So instead of having the 254 pounds of thrust, we dropped down to 52 pounds of thrust. It also took a very long time for the motor to build up to that 52 pounds of thrust, which is a real problem because that's when you're trying to get the rocket off of the rod, and you have to do that pretty quickly. So we don't really feel that this 10% additive is giving us certainly enough thrust, and the amount of burn time that we're getting out of it for the loss of thrust really isn't worth it. So I don't think we're really going to pursue much more on this additive to the fuel and trying to slow it down. Instead, what we're probably going to end up doing, I'm going to build another case because I want to make a little change so that we can fit the PVC in a little bit easier. Right now it's a little bit tight and we have to shave the PVC down. And then we're also working with this original nozzle that we've had for this entire series, which is working great, but it is a number 32 nozzle hole. And because we only got 254 pounds of thrust when we did the single cell, I really know that this case can hold up more because in a previous test we had about 360 pounds of thrust. So more thrust, more pressure. We know that this case can hold more pressure than we're giving it right now. So we're probably going to drop that nozzle down to either a number 30 or a number 28. We got to do some work and decide what we want to do there. So we'll drop that down. Once we do that, we'll be able to redo the case, a new single fuel cell, and do a thrust test on that. Hopefully we'll still get about the 1.6 second burn time, but we're hoping to get closer up into the 300 range for thrust. Hope you enjoyed some of it. Some of it was kind of funny, a little funnier than we expected. Thanks for watching. Don't forget to click the like button and subscribe as well so you get notifications. We are going to come out with some more videos real soon, hopefully with this and with some launches that we'll be doing this summer as well. So thank you for watching, and we'll see you next time.